Hey, welcome back. Today we're going to start looking at polar functions and multivariable. You might recall that we used polar functions last year in calculus, single variable, in order to help us find areas of certain curves. Well, today we're going to take a look at how we can use polars to find volumes, areas, all sorts of things using multiple variable functions. So we're going to start easily, okay? So let's say I have this function here, r of theta. It's already a polar function. And outside of it, I have these two radial arms coming from the center, intersecting my surface, or in case here my function, r of theta. Now, I want to find the area of this little sector. So to do that, I have to kind of think about the arc length right here. Because if I make two different arc lengths, S1 and S2, and if you kind of notice, they kind of look like a smaller piece I can start taking a look at. So I want to find the area of this little section in here. So to do this, I'm going to think calculus. Now we should remember that to get arc length, it's r times theta. But when we start thinking about calculus, we're going to let theta go to 0. And if we let theta go to 0, what's going to happen to S1 and S2? Well, of course, if theta goes to 0, these two are going to get more similar in length. Right now, they're not the same arc length, but as theta gets smaller and smaller and smaller, so does S1 and S2 until they approach the same exact value. So as theta approaches 0, we know, or can assume, that S1 approaches the same value as S2. And we're just going to leave that as S. Well, up here we have the change in radii, delta R1, delta R2. This is the small minute change in the radius from the center to the function itself. Well, R1 and R2, as theta go to 0, also become close to each other. So we can say that delta R1 approximate delta R2. And we're going to call that the change in R. Now, also, let's think about this. If these get smaller and smaller and smaller, these are kind of like straight lines already, but as theta gets smaller, we're talking about tangential lines here. So S1 and S2 kind of become linear themselves. So as theta go to 0, we also get this little region right here becomes almost a rectangle. Matter of fact, it basically becomes a rectangle. Where here we have my side, up here, I would have my side length. We call that S, which remember was r theta, which from now for us is going to be r, the change in r, d theta, as theta goes to 0. And the length right here, that's just delta r. Well, so there's my arc length, and there's my side right there. So we got our two sides of a rectangle. Now we know from earlier that dy dx, ready? If I want to find my area of my rectangle, it's going to be dy dx, dy dx, and I can rewrite that. Well, what did we say dy is? We call that delta r. And dx is r delta theta. So we can therefore now say that the area of this little tiny rectangle is r delta r delta theta. And as delta theta goes to 0, remember, if delta theta goes to 0, we're going to get r dr d theta. And this is our formula for area using using polars right here. And we call it actually dA for the change in area right there. So we're going to take a look at a bunch of examples. So if you want, go to the next video, we'll take a look. We will start applying this. See you then.